Hey guys, I have another exam question here for you. This one's on forces and friction, so we're going to be looking at things like free body diagrams, some momentum questions, balls swinging around, boxes being pushed, things like that. And this is a question that I actually set myself again a few years ago. And I'm going to tell you exactly what the examiner wants from you and how to get the most marks out of each question. And as usual, I strongly recommend that you pause the video, take a read through the question and familiarize yourself with what we're doing. Maybe try the question yourself. If you do try it yourself, you should be aiming to take about half an hour to finish the whole thing. So I'll take a moment so that you can pause the video and then we'll jump straight into the question. Now, when you're ready, let's start with question 1, part A, and let's see what this is telling us. So it says, a small box of mass m1 equals 2 kilograms sits atop a larger box of mass m2 equals 5 kilograms. The larger box is pulled across a flat, frictionless surface by a horizontal rope with tension T. The coefficient of static friction between the two boxes is μs equals 0.8. What is the maximum tension the rope may have before the small box slips from the larger box? Okay, so let's start with a picture. And I've already begun drawing our boxes here. So the top box is our small box of mass m1. So let's write that down. This is m1 equals 2 kilograms from the question. And the box below it is our larger box m2, which is equal to 5 kilograms. And what else do we know from the question? We know that these boxes are being pulled along by a rope, and they're being pulled horizontally, and our rope has a tension of T. So basically what we're looking for is the point where the force applied by the tension in this rope is equal to the force applied by the friction that this box feels, because the friction is what's keeping it in place here. So to find that, let's draw a free body diagram of our small box. And think about the forces that are acting here. So here's our small box, not quite as neat as it is above, but I think we'll live, and it's of mass m1. Let's write this in here. And now let's think about what forces we have acting on this box. So let's think about the forces up and down first in the y-plane. So downwards we have gravity, of course. Gravity is pulling this down with a force of m1 times g. So this is the mass of the box times the acceleration due to the Earth's gravitational field. And acting against gravity is the normal force. And the normal force is whatever is pushing this box up. So in this case, this box is being held up by m2, a bigger box, which is applying a normal force. And in the horizontal plane, in the x direction, our forces are slightly more complicated than this. So our whole system is being pulled forward by our rope, which means that it's accelerating. So our small box has an inherent opposition to acceleration. So this is just Newton's law, and this is the F equals ma law. So this box is opposing the force applied to it by the rope, and it applies an equal and opposite force of ma. So this is the mass of the box, this is m1, and this is the acceleration of the whole system. And then in the opposite direction, we have friction sticking this box down to our larger box, because the larger box is what's dragging it along and the friction is what's holding them together. And friction is just defined as mu, our coefficient of friction, in this case it's static friction, because we don't want our box to be moving, times the normal force n. So this is mu s times n. And this is our complete free body diagram. This is all the forces we have acting here. And now all we have to do is resolve our forces. So let's do that. Let's first of all draw in our coordinates so we know what direction is what. So this is what we will be working with. This is our x direction, and this is our y direction. And these coordinates are arbitrary, so our y and x could be pointing in anywhere as long as they're at right angles to one another. But I mean, it's conventional and it's easy to think about things in this just up, down, left, right sort of way. It's intuitive. So let's resolve our forces now. Let's think about which forces are acting in which directions. And let's start with y because it's the simpler case. So in y we have our total force Fy, which is equal to, so in the positive y direction we have n, our normal force, pointing upwards. So this is n. And in the negative y direction we have the force due to gravity pulling our box down. So this is just m1g, and we're just copying this down from our free body diagram. And this is all the forces we have in y. But what we know here is that our box is not flying away and it's not falling through the bigger box. It's stationary in y, which means that these forces must be balancing each other out. There's no greater force here. So our total force F of y must be equal to 0 because it's not being pulled in any direction in this plane. So our n minus m1g is also equal to 0. So what we can say, and this seems trivial, but it's important, is that n, our normal force, is equal to mg. So let's move this down here so I've got a bit more space. And this is everything we know about y. This is all of our forces in y resolved. So let's move on to our x direction. So in x, similar to before, we have total force F of x this time. This is the total forces acting in the x direction. And what do we have? In the positive x, we have our friction keeping our box stuck to our larger box. And this is mu s n. And again, we're just copying this down from our free body diagram. So this is the force due to friction. And then opposing this in the negative x direction, we have the box's opposition to acceleration. So this is just minus m1a. So we have friction minus the box's inherent opposition to acceleration. And we want to find the point at which this box is just on the verge of moving, the threshold. So this is the maximum acceleration that the box can feel before it starts to slip. And what this means is that our friction, our mu s n, is perfectly balanced with our opposition to motion, our m1a. So again, because they're perfectly balanced, this equals 0, because we just have friction minus opposition to acceleration. So what we can say here is mu s multiplied by n equals m1a, because we've just rearranged our equation here. And another thing we know from our forces in y is that this n is equal to m1g. So if we just replace our n, we can write down mu s m1g is equal to m1a. You see, we've just taken our equation here and we've replaced our n with m1g, and we get this expression. And then we can cancel these m's by dividing through by m1. So we just divided both sides through by m1. And now we have an expression for the acceleration, the maximum acceleration the system can take before our small box starts to slip. And this is what we're looking for. So we get our acceleration is equal to mu s, our coefficient of static friction, times g. So now what we need to do is relate this to the tension in the rope. And the way we're going to go about this is by again drawing another free body diagram, but this time of the whole system, so that we can see exactly how the tension of the rope affects the acceleration of our system. So let's get that drawn down. We have our small box on top of our large box, And this is one whole system now, so we're considering the mass of the entire thing. So let's just say this whole thing is a new mass of mt. So this is the total mass of our system. And this mt is just m1 plus m2, right? Because it's the mass of the small box plus the mass of the larger box, which is just 2 kilograms plus 5 kilograms, 7 kilograms. So let's just write this in here. 7 kg. And let's think about the forces that are acting here. So again, pulling this box down, we have, that is not a good arrow. Pulling this box down, we have mt this time, so this is our total mass, times g. So this is the force due to gravity, pulling the whole thing down. And again, we have the normal force acting in the opposite direction. And now this time we have some different forces acting forwards and backwards. So this time we're looking at a rope pulling this box forwards. So the rope is pulling our box forwards, and this rope is acting with a force equal to the tension in the rope, which is just T. And this T is what we're looking for, remember from the question. We're looking for the maximum tension the rope can take before our small box starts to slip. And then pulling this in the opposite direction is our whole system's opposition to motion, which is just mta, as before, from Newton's law. And there's no friction term here, there's no friction coefficient, because our question states that we're pulling our box across a horizontal frictionless surface. But if you did have a friction term, you would just simply sum the friction of the larger box onto the opposition to motion. So we'd have an extra term pulling it back against the tension. But in this case, we don't have to worry about that because there's no friction here. And I mean, I know I've drawn this box kind of wonky here, but please imagine this is on a horizontal surface. So we're pulling this along a flat surface. So let's, as before, resolve our forces. Let's start with y because it's more simple. In fact, let's define our coordinates again here. And again, these coordinates are arbitrary. But now it's not just convention that we're sticking to, it's consistency. Because before I defined my coordinates, up here is y and x, y pointing upwards and x to the right. So I'm going to be consistent so that our answer is consistent. It makes sense. There's no negatives where negatives shouldn't be. So let's start resolving these forces, and we'll start with y again. So in the y direction, we have a total force Fy, which is equal to n normal force in positive y, exactly the same as before, minus mtg. So this is the force opposing the normal force. This is gravity pulling our box down. And again, our box isn't flying away and it's not falling through the floor. So this whole thing is equal to 0 because our forces are balanced. So n this time equals mt, our total mass, 7 kilograms, times g, the acceleration due to the Earth's gravitational field. And this is y completed. So let's move on to x. And again, the same as before, we have forces in x, total force in x, Fx is equal to, and this time we have in the positive x direction, tension T. So this is what we're looking for, our tension. And opposing it is the box's inherent opposition to acceleration. So this is just Newton's law. So this is in the negative x direction, it's minus mta. And as in all the other cases, the opposition to motion is equal to our tension here, because our tension is creating this opposition to motion. So our forces are balanced, so this whole thing is equal to 0. So what we can say is T equals mt a, the acceleration of the system. And what we're looking for is the maximum acceleration before our box slips off, or the maximum tension rather, before our box slips off. And we have this expression for tension here, which is MTA, and we have an expression for the maximum acceleration our box can feel before it starts to slip. So all we have to do is sub in this A that we found earlier into here. So let's see what we get if we do this. This is equal to MT mu S G. And we know what all these things are, right? We know our total mass is 7 kilograms. We know mu S is 0.8 because the question tells us, and we know that the acceleration due to the Earth's gravitational field is 9.81 because we just know that. So let's write these things in for completeness sake. 7 kg times 0.8 times 9.81 meters per second squared, because this is an acceleration, right? This is the acceleration due to gravity. And if we put that into a calculator, what we're going to get out is 54.94, I'm sorry, that's point, kilograms meters per second squared. And this is good because kilograms per meter second squared is actually newtons. So this is a force, so we know we've done the right thing here because we're looking for a force. And this is our final tension, and this is what our question is asking for. So that was a nice easy question. And let's see how many marks we got for that. That's 8 marks out of 25, so we got almost a third of the marks there, just for this simple question. We drew some free body diagrams and we resolved forces, and we ended up with our final answer. A couple of things to note are, maybe it doesn't seem like it in this question, but free body diagrams are incredibly useful. And if there's nothing else you take away from this video, it should be that you should always draw free body diagrams, because you don't have to even think about what's happening once you've drawn a free body diagram. You just write down your coordinates and you look at the picture and you write down what you see. And it's kind of easy to imagine what forces are acting here without a free body diagram, but in a situation where maybe you have a hill and a box is here and then somebody's pushing the box up the hill, oh dear, and you know your forces are all over the place and they're at different angles. It's kind of hard to see what's going to happen, but once you draw a picture, things are just crystal clear. It's wonderful. And beyond that, there's not really much to say about this, other than, again, this coordinate system is arbitrary, so your y can be pointing in any direction, but it's just convenient to have your y pointing upwards and your x pointing to the right. As long as you're consistent, though, it doesn't matter, you'll get the same answer. So that's the end of part A. Now let's move on to part B. And what do we have here? So it tells us a sphere of mass m equals 5 kilograms is tied to a pole by 2 strings of length L equals 10 meters. The sphere travels in a circle around the pole at a speed of v equals 30 meters per second. Find the tension in each wire. See figure 1 for setup. And this is our figure 1. So here we have our ball attached by 2 strings to a pole, and our ball is spinning around at a velocity of v equals 30 meters per second. So initially this question looks quite scary compared to part A, because we're dealing with 2 tensions here pointing in different directions, and they're both at angles to our x and y, so they're not pointing directly in any one direction. But what you'll find is that once we've drawn a free body diagram, things will become very easy. So we're on part B. And let's get this free body diagram drawn up. immediately before we even think about what we're looking for. So we have our ball here and it's red. Let's be true to the question. And let's think about the forces that are acting on our ball. So our ball is being pulled down, as always, by the force due to gravity, which is mg. So m is the mass of our ball, and g is the acceleration due to gravity as before. And we have two tensions here holding our ball due to the two pieces of string. So we have a tension pointing this way, which we'll call T2. So this is from our second wire down here on our picture. And we have one going off here, and we'll call this T1. So this is the tension due to wire 1. And our ball is spinning around in a circle, right? It's spinning around our pole. So we have a centripetal force as well, which is pushing our ball out. And this is what our tensions are pulling against. So our centripetal force is in this direction, because our ball is spinning like this. So our velocity is in this direction. This is our v. Let's get rid of that because it's confusing for our free body diagram. But we have a force due to that velocity, and this is a centripetal force, Fc, which is equal to m, the mass of our ball, v squared, velocity, over r, where r is the radius of the circle that this ball is making around the pole. So now we see what we need to answer this question. And the only thing we don't know here is the angle that these tensions make to the horizontal. So we'll call this theta, and this is going to be what we're looking for. We don't know this angle, and we don't know our radius. We don't know the radius of the circle that this ball is making. But these are really easy to find if we just think about the setup. So let's move this down here a little bit. And let's think about how this ball is traveling around. So let's draw this again. So these aren't forces this time, these are wires. And this is the triangle that our wires make, and this is our ball on the end for completeness. And we know that this is L equals 10 meters. And we know that this is L equals 10 meters, so these wires are the same length. And if we look at our original question here, we have a separation between these wires of 10 meters. So this is an equilateral triangle. So let's just draw that on here. And this is 10 meters. So let's think about what we're looking for here. This is our pole, this 10 meters is our pole. And we want the angle here, theta, because this is our angle between our tensions and our horizontal plane. So we want this theta, and the theta is the same on both sides, because this is a symmetric system, so this is theta and this is theta. And we want this length r here, because this is the radius of the circle that our ball is making. Because our ball is this far from the pole and it's travelling in a constant circle around. So we've split this up into two triangles now, and let's just draw that explicitly. A lot of triangles here. So this is just half of this picture to make it clear what we're doing. And now we have a right angled triangle, and this side is half of this separation, so this is 5 meters because our system is symmetrical. And we know the system is symmetrical, by the way, because we have the same L for each string. So this has got to be the same on each side because our strings are the same length. And this is our theta, and this is our R, and this is L, which we know is 10 meters. So we have enough information to get everything here now. Let's move this down. So first of all, let's find R. And to find R, we're going to use just a little bit of Pythagoras. So remember, Pythagoras involves the sum of squares on a triangle. And what we have is r equals the square root of the hypotenuse minus the side that we know. So the hypotenuse is 10 meters squared. So let's square this meters as well. Minus 5 meters squared, and this is all square rooted. This is just Pythagoras, this is stuff that you should know. So if we put this into a calculator, we get the answer r equals 5 root 3. So that's our r dealt with. And we also need our theta. And for our theta, we're going to use trigonometry. So we're not going to do theta equals here. We're going to remember trigonometry. So we have our hypotenuse, and we have the opposite of our angle. So if we remember what sine is, our definition of sine, we have sine theta is equal to the opposite over the hypotenuse, which in this case is 5 meters over 10 meters. So let's just put that down, 5 meters over 10 meters. And now we want to isolate this theta, we want to find out what theta is. So what we're going to do is we're just going to act the inverse sine on both sides of this equation. So if we act the inverse sine on a sine, we just get the interior. And the interior in this case is theta, so we have theta equals, and then we're acting the inverse of sine on the other side, so we have sine to the minus 1. And remember, this isn't 1 over sine, this is arc sine, or a sine. Sine minus 1, 5 over 10. And we're just forgetting the meters because they've been divided out here. And this is equal to 30 degrees. So our theta is 30 degrees. And now we know everything that we need for our free body diagram, right? All we needed was our r, our radius, and theta. So let's move down here and start this again. Let's draw our free body diagram with our new information. First of all, let's copy down what we found out. So we know r is 5 root 3, and we know that theta is 30 degrees. And let's just copy down our free body diagram again. So it's the free body diagram of our ball. And we have gravity pulling our ball downwards. Oh, that is not a good arrow either. We have our ropes. So we have a rope pulling this way. And this is T2. And we have a rope pulling in this direction with a force of T1. And then again we have our ball spinning round in a circle, so we have a centripetal force pushing our ball away from our pole, opposing the tensions in the string. And this is going to be mv squared over r. And now we know everything that we've got here, so let's just draw in our line so we know our angle. This is 30 degrees. Let's put theta equals 30 degrees here. So let's begin by drawing our coordinates again, and then we can resolve these forces. So we have x moving positively in the right direction, and y positive up. So let's resolve these forces. Let's start this time with x because we've defined our theta from x. So it'll be easier to see what's happening now with x. So we have in the x direction a total force Fx of, so we have mv squared over r pointing in the positive x. So we can just copy that down directly from our free body diagram. So this is mv squared over r. And then in the negative x direction, we have some component of these tensions. So let's draw a picture to think about exactly what component this is. Oh, I'm sorry. So let's draw a picture to think about exactly what component we're looking for. So we have our tension here, T1, and we can split this up into two components, an x and a y component. So the y component goes this way. This is our y component. And our x component goes this way. And this is our angle, theta, as before. So immediately you can see that this looks like a right-angled triangle here. So let's just draw a line here so you can see a bit more clearly. And now you should be able to see this is what we want. The adjacent angle is what we want here. The adjacent length is what we want here. So our x component of the tension is just T1 cos theta, right? Because cos theta is defined as the adjacent over the hypotenuse. I'm sure you guys know this. So we know now we're looking for T1 cos theta here. This is the force acting in the x direction due to tension. So let's get rid of this and make some space. So we have mv squared over r minus, because this is acting in the negative x direction, T1 cos theta. And we know that the angle here for our T2 is also theta. This whole thing is symmetrical. So this is minus T2 cos theta as well. Because it's pulling in the same direction. It's pulling in the same x direction. So this is our total force on x. And the whole thing is balanced because our ball isn't moving in this direction and it's not moving in this direction. It's not falling and it's not breaking the strings. So our forces are balanced here. So this whole thing is equal to 0, this whole term is equal to 0. And what that means is we can move our t cos thetas, onto the other side of the equation. So what we end up with is mv squared over r now equals T1 cos theta minus, plus T2 cos theta. So we've just summed T1 cos theta minus T2 cos theta onto both sides. And let's tidy this up a bit by dividing through by cos theta. So we end up with T1 plus T2. There's no cos theta here because we've divided this side through, equals mv squared over r cos theta, because we've divided one side through by cos theta, so we have to divide the other side through. So here we have an expression for T1 plus T2, and I went through this kind of quickly and skipped some steps, so maybe it's a good idea for you to work this out yourself if you don't see it. But now let's move on to the y direction, because we're finished here. So in y, we have Fy, the total force in y, this should be getting familiar now, equals So in our positive y direction, we have a component of t1. So let's draw our picture again and remind ourselves of what we're looking at here. This is t1. And this is our y component, and this is our x component, and this is theta. Now, it's not so obvious when we're dealing with the y component here, but we're just looking for the magnitude of y here. So what we can do is we can shift our y component over here. So this is now our y component. Oh, geez, that's an arrow, but you get the picture. This is our y component here. And this is now the opposite side of our triangle, our right-angled triangle. So because it's the opposite, we're looking at sine, which means that in the positive y direction we have t1 sine theta this time, using the same logic as we used to find the x contribution from the tensions. So we know we're dealing with a sine here in the positive y, sorry. And let's delete our little picture here and write this down. So in the positive y we have t1 sine theta. And now this time our t2, our y component of t2 is opposing our x component of t1. And again it's symmetrical, so it's going to be a sine, but this time it's just pointing down. So we have minus t2 sine theta. And finally we have the force due to gravity, again pulling this ball down in the negative y, so it's going to be minus mg. This ball's not falling, it's not going up, it's balanced. So our forces are balanced, which means that the whole thing equals 0. So this time we're going to say t1 sine theta minus t2 sine theta is equal to mg, so the force due to gravity. And let's move this down a little bit. And again, let's divide through by sine so we get our tensions isolated. So we have t1 minus t2, so just divided through by sine again, equals mg over sine theta. So these are our resolved forces, and we're looking for tensions. Sorry, this should be t2. We're looking for our tensions here. And we have two equations with two tensions. So we have simultaneous equations. We can solve this using simultaneous equations. So let's write down our equations separately over here. t1 plus t2. So this is the first one we found, equals mv squared over r cos theta. And this is equation 1. We'll call this equation 1. And the second one we found was t1 minus t2. This is the one we just did in the y direction, equals mg over sine theta. And this is equation 2 now. So now we're just solving simultaneous equations. And I think what we're going to do is, I'm going to take equation 2 and I'm going to find an expression for t1 here. So let's rearrange equation 2 for t1. So we get t1 equals mg over sine theta plus t2. So we've just moved our t2 here in equation 2 over to the other side. And now let's sub this expression for t1 into equation 1 here. So we're going to replace T1 with this. So we get mg over sine theta plus T2. Let's put a bracket around this so it's obvious where this is coming from. And then this is sum to T2 here in our equation 1 equals mv squared over r cos theta. I'm sure you guys know how to solve simultaneous equations, but I'm just going through this for completeness. And then let's rearrange to isolate T2. I'm going to skip some steps here because it's quite tedious, but I'm sure you guys can figure this out. So we have T2 on one side equals mv squared over r cos theta. So that's just this part here. And then we've subtracted mg over sine theta from this side. And then we have two t's here, two t2's here. Oh, what a mouthful, two t2's. So we're going to have to divide the whole thing by 2. So this is all multiplied by 1 over 2. So there you go, T2 equals half mv squared over r cos theta minus mg over sine theta. And if we put the numbers into a calculator, we end up with 250.95 newtons. So this is our T2. So we're halfway there now, we just need T1. And to find T1 is really simple, now we've got this T2. So let's take our equation 1 again and just sub in the T2 we've just found. So let's take this equation we have for T1, let's call this equation 3. Just for clarity, we're going to take equation 3 and we're going to sub our new T2 into it. So let's see what we get. We get T1 equals mg over sine theta plus our new T2, which is 250.95 newtons. And this is equal to 349.05 newtons. So we have T1 and T2. Let's write these down properly. T1 equals 349.05 newtons and T2 equals 250.95 newtons. And this is what our question is looking for, and let's just have a look at these answers and see do they make sense. So T1 is the tension of our wire, our first wire, our wire 1, which is pulling the ball up against gravity. And T2 is our tension that's just holding our ball into the pole, stopping it from flying away further. So we would expect that T1 in this case is bigger than T2 because our wire 1 is holding the ball and pulling it back in. And this is what we see here in our answer. We see that our tension 1 is higher than our tension 2. So our answer makes sense. And both of our forces are positive, so that makes sense. They're both pulling the ball back in. And so you should be pretty happy with this answer. These are our final answers. And this is what the question is asked for. Find the tension in each wire. So this is 9 marks that we've just completed. We're 2/3 of the way there, almost finished. And again, there's not really much to say about this question. it really does show you how useful a free body diagram is, because I don't know about you, but just doing this in my head and thinking about these angles, it gives me a headache. But being able to look at a picture, seeing a triangle here, realizing that these things are just causes and sines, it really makes life a lot easier. And again, if you expect something out of your answer, so we expect that T1 in this case is going to be bigger than T2, then check it. Just make sure that your answer makes sense. And again, you can check the coordinates. And you can also check your units. So I didn't check it in this case because I'm pretty sure that I got it right. But you can check your units and make sure you got newtons in the end. And then if you don't get newtons, obviously something's gone wrong. You've missed some unit out somewhere, or you've done part of the question wrong, and you can go back and check what you've messed up. So it's always good to check your answers if you have something that you expect. And that's the end of part B, so let's move on to our final question, part C. Now we're going to speed through this part of the question because I think we're all experts here. So we're on part C, and let's see what we've got. So a projectile of mass MP equals 3 kilograms is fired horizontally and hits a ball of mass MB equals 30 kilograms, sticking to it. The ball is suspended from a wire which can withstand a maximum tension of T equals 900 newtons before breaking. What is the maximum speed the projectile can take without the cable breaking? So let's draw up our system here very quickly. We have our ball on a string, and this is of mass MB equals 30 kilograms. And we have a projectile coming towards it of mass MP equals 3 kilograms. So let's start with a free body diagram. And we're going to be considering our... Oops. Oh man, everything's going wrong. So let's start with a free body diagram. And we're going to be considering the system after the projectile has hit the ball, immediately afterwards. So our ball hasn't had time to move yet, but it does have a velocity. So let's think about what forces are acting on it. So let's quickly draw our coordinates. This is x, and this is y. So acting upwards, we have the tension from our rope. So this is tension T. And then opposing this, acting downwards, we have the force due to gravity. So this is MP plus MP, right? Because now we're looking at the total system. We're looking at a projectile stuck in our ball. So this is the two masses summed together, MP plus MP, multiplied by the acceleration due to Earth's gravitational field, g. And our ball now has some velocity in this direction, right? This is our final system's velocity after the ball's been hit by its projectile. So it also has a centripetal force pulling on the rope, which is MP plus MB, so the total mass again of the system, times v squared over r, where r is the length of this rope. So that's all the forces we have acting here. There's nothing in the x direction because the ball hasn't had a chance to move yet, so there's no component of gravity pulling this back. So let's resolve forces in y. Just the same as we did before, y has a total force, Fy, which is equal to T, the tension in the rope in the positive y direction, minus this contribution from gravity and centripetal force. So let's factor out our MP plus MB term. MP plus MB. This is factored out. And we have the force due to gravity, so mg plus the force due to centripetal acceleration, which is v squared over r. And there you go, this is the force in y. And our rope is just on the point of breaking because we're looking at the point where our ball has enough velocity that our rope is just about to break. So our forces are perfectly balanced here, and we have this whole thing is equal to 0 because our ball isn't falling, it's not going up. So what we can do is we can write that T equals MP plus MB times G plus v squared over r. And what we're looking for here is this v. We want the velocity of the system at which the rope is just about to break. And that's at 900 newtons because that's what the question tells us we're looking for. So let's rearrange this for v, and let's make this T max, where this is 900 newtons, and we'll make this one T max too, to be consistent. So let's rearrange this now. So we have v, the velocity of the system, is equal to T max over MP plus MB minus G, and this whole thing is square rooted, and these terms are all multiplied by, a bit messy now, but you can still see what I'm doing. These terms are multiplied by r, and this whole thing is under a square root. And I'm skipping out a lot of steps here because we've done this a million times now, and I think you guys understand what's happening. So this is the final velocity of our system. And now let's try and get a better idea of what's going on by drawing our initial and final system. And you should hopefully be able to see that what we're going to do is consider the momentum in each case. And we're going to use the conservation of momentum to tell us what our initial velocity of our projectile is. So this is our ball on a string, and this is our final system, so this has got a projectile stuck in it. And it's of a mass, let's call it the final mass, and this is MP plus MB, and this is equal to 33 kg. And its velocity is the one that we found up here, and I'm not going to write this down again. Just remember that this is the final velocity, this v. So this is our final system. Let's call this 2. And this is our initial system. Let's call this 1. So we have our projectile coming in. So it's got a mass MP of 3 kg, as before. And it's got a velocity vi. So this is the initial velocity of our projectile. And we don't know what this is. And this is our pendulum. This is our ball on a string, should I say, with mass mb equals 30 kg and a velocity, let's call it vb, equals 0 because it starts out stationary. So these are our two systems. So let's consider the momentum of each case. In our first case we have the momentum of our projectile, which is mp, vi, what we're looking for here is vi, plus mb vb. So immediately we know vb, the velocity of our ball, initially is 0. It's stationary, so we can just set this to 0. So our momentum term initially is just mp, the mass of the projectile, times vi, the initial velocity of the projectile. And this is equal to our final momentum through conservation of momentum, which is just mt v. So let's move this down here. And we know everything here except our vi, which is what we're looking for. So let's rearrange this to find our initial velocity of our pendulum, our projectile. So this is vi equals mt v, where v is the final velocity of the system, remember, over mp. And we have a v up here, so let's put this in. We have mt, sorry, and then we sub in our v here, so this is square root r times T max, so this is 900 newtons, over, so let's put in mt here as well, minus g. And this is our expression for the initial velocity of our projectile, but I've just realized that I didn't give a length of the string that this ball is suspended from. So let me just draw an amended picture here and I'll edit this into the actual exam. So our ball is suspended from a string, and this is what we're looking at. So our string is of length L equals 1 meter. So this is the R that we're dealing with here from our centripetal force. So now we have all the information we need, and all that's left is to put the numbers into this expression, which I'll leave to you, and crunch the numbers, and we get that vi, our initial projectile velocity, is equal to 137.9 meters per second. So it's traveling pretty fast. And again, you can check your units to make sure you have meters per second here if you're not sure about the answer. And that's it, that's all the question's asking for. And now we've got all of our questions finished. So if you were doing that yourself, you should have been aiming to take about half an hour. Obviously I took a little bit longer because I'm explaining it as I go. But hopefully you found that easy enough and you understood my explanations if you got stuck anywhere. And I'm going to end the video there, so stay classy San Diego and good night.